Alright, let's see if I can do a good enough job explaining this to where somebody could use it, or at least understand the whole process enough to know what the fuck I'm doing. The way the 24x crank signal works, it gets interpreted into a bunch of zeros and ones based on whether it's a short tooth or a long tooth. You keep track of short and long, and you end up with a pattern. This is that pattern. You would figure out what that pattern is at like max advance, because you can't do anything negative numbers. It's all just delays from a set point. No negative numbers. ECUs that use negative numbers do a bunch of math and turn it into positive numbers. That's just how this works. We're talking laws of physics. You can't time travel. How much there is I need to explain in here. There's a bunch of averaging. Let's just go straight to the tunable stuff. I added some comments in here. Low KPA, high KPA. It also doesn't talk KPA. It depends on whatever the hell your map sensor is. Here's RPM though. You get exact numbers for that. 17 by 17 tables. It was originally going to be 16 by 16, but part of doing bilinear interpolation is you get a value, and then you get the +1 of that value. The index +1 gets next row or next column, and then you do some math there to go between them. And I'm actually getting, here's this value. I grab these three, interpolate between these, and then interpolate between those two results, so you can end up right in the middle somewhere. And then that interpolated value gets some temperature adjustment, percentage based. I thought about doing plus and minus, but you know what? No. If you need plus and minus, then do the percentage accordingly. You'll figure it out. Or you can just comment, uncomment. There you go. Spark doesn't change with temp. You can do the same thing up here for fuel. Rev limiter. I could do something like how I updated my signal generator here. 2.5 million divided by RPM you want, and that's what this variable gets set as. But if you're not willing to pull out a calculator, this ain't the ECU for you, because there's no third-party tuning software for this yet. So let's say you want 6,000 RPM. 2.5 million divided by 6,000, 416, 417, close enough. Let's just test out that number right now. 417. Bigger numbers equal slower, by the way. Save. Oscilloscope. We're at idle right now. It's 6,050. Upload that to my signal generator running on an ESP32. Let it compile and upload. There you go. Here's cam signal from the signal generator, which my ECU doesn't use, but it's evenly spaced, so I can use it as a trigger to keep things still. Right now, injector pulse width is at 100%. Let me turn down my map sensor input. There you go. You can see the pulses. Now let's update the ECU with its new rev limiter. While that's uploading, let's do math on what RPM this is. 5382, 53.82 times 120, 6,400. What did I fuck up? Oh, I'm on fuel. I need to put the oscilloscope on the spark output. Alright. No spark. Now let's set it to 5950. Upload. Alright, now we're going to go back down below the rev limiter. When the signal goes away and then comes back, you'll start seeing the pulses. There they are. Actual RPM 49.26. $59.11. There's margin of error on my signal generator. Let's see what having it right at 6,000 is. If it's going to barely overshoot or barely undershoot. Close, really close. 49999. Real close. Let's try 5990. So see there, I went with a number set. Well, there was decimals and I rounded up, which means slightly slower. We're at 59.99 and spark cut is engaged. Alright. $49.62 614. There you go. That's a pretty small window, right around where we set it, and it's functioning. There's also a low RPM fuel cut. You just take my word for it, it's working. Fuel does not cut off with the rev limiter, just spark. Let's see here. There's some timing change. If it gets close to wrapping around 360, it does cut off the spark. So that's one of the things you got to keep in mind when you're setting your initial pattern match. If you actually want like 10 degrees of retard for certain situations, then well, whatever, you got plenty of leeway. I'll hold off on exact instructions for that initial pattern match until I actually test it myself. It's gonna be a while. Go back to fuel here. Alright, fuel output. There's a map sensor doing its thing. Pulse width gets higher, end of injection doesn't change. End of injection trim. That's a good one right here. With RPM, showing you where low and high RPM is. Right now it's set to half a millisecond, 500 microseconds. And once I get up there, you can see the end of the pulse actually moving over. So once it's necessary to hit 100% injector pulse, end of injection timing gets overridden. I needed something because that initial pattern match, which is where the end of this line is, gets you plus or minus 15 degrees. And if that's good enough, then you can either ignore this table, set it at all zeros, whatever. What other things are worth going on about? There's the rolling averages, which down here 24, and then their corresponding shit up here. This one's a map sensor, RPM, IAT. To cut down on sentencer, like input latency, you could cut these down 12, 6, whatever works, in combination with hardware filtering and whatever else. Moving on. Here's the high and low spark cut. Rolling average. EDC index. There's fixed point math. That's where there's this bit shifting, and then alright, there's a good way to explain. The rolling average RPM time average here, microseconds per 15 degrees, gets divided and multiplied to get you 1 through 16 for indexing these arrays. But there's also a remaining decimal, which is here, frac. And a decimal, fractions, the shit after a decimal point, is the same as a percentage. So the index on the arrays and the percentage between those indexes, pretty simple to do some interpolation math. Good luck reading through this and figuring out the variables. I just had to name them fucking something different from each other. So I went with terp instead of spelling out interpolation, whatever value, this other value. Sorry, it's not super readable. First big project. The signal generator was the first scratch built code project I ever fucking did. And this is the second. There's a lot more going on here. All this shit versus this. But it functions. Tuning's gonna be a bitch. End of injection trim. Also with interpolation, that same frac number calculated earlier. Frac used a bunch of times. A separate frac number, because this is between, this is this axis, not that, so a different fractional value there. Here's the if RPM below. Just sets pulse width to 0. And this part of the code was pretty early on, and I haven't looked over it much. All this down here, entirely AI generated. I told it how I wanted the pulses to behave. It spat out some code. I tested it. It worked. So that's awesome. Including these variables here it spit out. I had to take what was originally here, move that variable up to the start of my interpolation code, and then the output of the interpolation code and put it here. It was kind of tedious. I think I already mentioned that the crank sensor stuff it's in an interrupt, because you got to be precise on that, otherwise everything's going to be off. So it goes there, interrupts anything else that's going on. Tested this at speeds that even with all this interpolation code and everything, I've tested this at speeds faster than you can run an engine, so it's doing okay. Never put in decimal numbers in any of this. I'm pretty sure it won't even compile. It'll just refuse and say, what the fuck are you doing down here? Don't put in negatives. Again, it's all just starting point, and then you're adding delay. Max advance would be having a 0 in here, and it just does shit immediately. I should rename this D-start to spark timing or something, but then I gotta go through all this and change every mention of D-start. Originally I had 4 giant tables in here. It was D-start, D-end, and I-start, injector start, I-start, I-end. It was a mess. There was a measurable, like, microseconds, like sub 50 microseconds better timing control with the 4 big tables. But then I realized I could do, where is it? Oh god, I'm gonna keep track of all this shit. Oh, down further, here we go. Predicted 360 time. The amount of microseconds it takes for a full revolution, because RPM time per 15 degrees that gets measured, times 24 teeth, full 360 degrees, predicted 360 time. And then just subtracting and calculated, interpolated injector pulse width from all that, subtract it from full 360 time, and that's the amount of time that it waits to turn on the injector. That's how that works. And again, since you can't do minus and whatnot, for spark timing, there's wait time before you turn the coil on, and then there's the fixed 4 milliseconds of dwell, and then when it turns off is when you get spark. Part of the hassle with this is converting microseconds to how many degrees that's going to be at the different RPMs, because obviously at different RPMs it's a different number of microseconds per degree. Again, other ECUs are just doing the math for you in them when you plug in easy tuner numbers into a VE table. This doesn't do any of that. I plan on having that all done in some third-party software that then spits out the microsecond numbers you need to paste in here. Don't hold your breath for that though. I think I've gone over enough. I hope it may not help you read all the code, but I don't know, I explained it. Now, this line here is important for not overflowing the arrays here, so you don't get some goofy ass numbers. This limits it to 0 to 16, because even though there's 17, again, part of the interpolation is whatever number is calculated plus 1 to get to the next number in the array. Yeah. One good update I'll probably do is figure out, I'll put some kind of variable here and then move the patterns into here. Eventually I want to just be, this tab is all you fuck with. And you just leave this alone. And then you just save, Control S, sketch, upload, and there you go. Anyway, I think I've rambled on enough. Peace.